All right, so now that we have the basic operation of the ideal gas law and understanding a relationship, hopefully in an intuitive way, we can use that tool to help us think about the stoichiometry of gases in certain reactions. And one of the reactions that we can look at is a really industrially relevant one, which is the decomposition of this compound NaN3. So the question is, how many liters of nitrogen gas at this pressure, 1.15 atm and 30 C, are produced by decomposing 45 grams of sodium azide. So this reaction looks like this. 2 units of sodium azide, solid, that decomposes into sodium metal plus 3 moles of nitrogen gas. This reaction is something that hopefully you've never experienced before, but you may have. This is the reaction that responds to shock or electrical current, or really any energy input, to produce gas in an airbag in a vehicle. And so it's shock sensitive or acceleration sensitive. Often this is combined in a circuit with an accelerometer and an energy source. An accelerometer notes very rapid changes in velocity or acceleration in different directions, and in doing so it may send a current through this thing which will forward this reaction. What you get out of this is a whole bunch of nitrogen gas. So if you've got a tiny little pebble of this stuff inside of a deflated bag, maybe there's your bag deflated, there's your pebble, you initiate this reaction, what happens is the rapid expansion of this bag to contain the gas. And so this is a really important reaction industrially, and people use the ideal gas law all the time to figure out, well, I've got my new vehicle, how much or what mass of the azide compound do I need to incorporate here for the volume of the bag once it's inflated, so it doesn't rupture and explode in somebody's face, but also so it doesn't underinflate and not serve its purpose. So let me show you a quick video of this.
Hey, so Chris has his special car here. Okay, I hope you like his special car. He spent ages making it. And it's used his partner's furry dice here. I hope she didn't mind. Anyway, so she didn't have much choice. Anyway, so now on the car, somewhere in here, we have the steering wheel, and in the steering wheel there is an airbag. Now this airbag contains a compound called sodium azide. This is sodium combined with nitrogen. But again, this isn't a very stable compound. Really, the nitrogen wants to combine with itself instead to form the very stable nitrogen gas. So we're going to count down in a moment and see if we can set this airbag off with an electrical current. Now, it might be quite loud. Some of you might want to put your fingers in your ears if you don't like loud bangs. It's not too bad. Okay, so we'll have a countdown from 3. You need to watch very carefully, because if you blink, you'll miss it. 3, 2, 1. There, very good.
Okay, so very similar to our actual, the previous problem that we did as an example. There's just one stoichiometric step that we need to deal with here. So probably the first thing we need to do is figure out if we've got 45 grams of this stuff, we need to figure out what volume of this stuff that we get, right? So probably that's going to be convert this to moles, relate that to moles, and then convert that to volume using the ideal gas law. So one really simple step to get from here over to here. So let's do that really quickly. Pause the video, see if you can work that out yourself. All right, so I worked out the dimensional analysis here. I took the 45 grams that we were given, used the molecular weight of sodium azide here per mole of sodium azide. So the grams go away here, and then I related stoichiometrically, and actually this should be a 2 here, now that I look at that. 2 moles of sodium azide for every 3 moles of nitrogen gas computed. So these moles and these moles go away, and we're left with moles of nitrogen. Double check my numbers. That looks like 1.04 moles to me. And so we are right here in the process, and now we just need to equate what the volume of that is, and we know that the relationship between N and V is through the ideal gas law, PV equals nRT. We know the temperature is 30 C. We know the pressure is 1.18 or 1.15. We know the N constant for the gas, and we can compute this value. So let's pause the video and see if you can compute that value. Okay, I've set this up in the ideal gas law again. So I've got V equals nRT over P. So I got 1.04 moles. Oops, that goes away with moles here. I've got 30 plus 273.15 to get to Kelvin, because we're given this in C. So the conversion again is 273.15. So Kelvin goes away here, atmosphere goes away here. We're left with units liters, and that's going to give me 22.5 liters. And so when you have 45 grams of sodium azide, that should inflate to a volume of 22.5 liters at a pressure of 1.15 atm, which is part of the engineering choice. And the temperature is operative because there's some heat that's going to be emanated through the thermochemistry of this. So the temperature of the gas is probably a little bit higher than room temperature. The pressure of the bag can probably sustain a little bit more than atmospheric pressure, so it's a little bit greater than 1, and you get a bag size that's about 22.5 liters.